Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Find the longest substring containing vowels in even counts. In this problem, we are given a string S and we should return the size of the longest substring containing each vowel an even number of times. Then in example 1, for the given string, output is 13 because the longest substring we find with even number of vowels is this one and the length of the substring is 13. In this, E occurs 2 times, I occur 2 times, O occur 2 times, and if we extend the substring either this way or this way, the number of vowels will become odd. For example, if you go this way and add O, then number of O's will become 3, so it will become odd. If we start from here, then number of E becomes odd. So this is the only valid longest substring with even number of vowels. Similarly, in example 2, lead C with 2 E's is a valid longest substring. Finally, in example 3, string does not have any vowel at all. So that's why it is a valid longest substring because all the vowels occur 0 number of times and 0 is an even number. Now, in terms of solution, the naive or brute force approach can be that we generate all possible substrings and check each one of it to see if it has even number of vowel, and then we choose a substring with the longest length that satisfies the condition. The time complexity to generate all the substrings will be O of n square because we will be using 2 loops and iterate over the string and generate all the substrings between the pointers I and j. And then we have to check each substring for an even number of vowels, and that will take O of n for each string, so that the time complexity becomes O of n cube, which is computationally expensive. Another approach that I was initially thinking was using sliding window technique. However, it quickly became clear that it is challenging to know when to shift the left pointer. For example, consider the input string from example 1 and focus on the vowels. Initially, left and right pointer will be at the start index, and now we extend our window with the right pointer. And suppose our right pointer is at the secondary, so our substring is valid with even number of vowels. But now we extend our window and we encounter a third E, which makes the number of vowels odd. Then which E should be removed to maintain the even counts? For example, if I move my left pointer here and exclude an E, and later we find out another E in the string, then the count becomes even again. So this makes it difficult to apply the sliding window technique. So now let's look at the problem again. We just need to check if a substring has even number of each vowel. We don't care about the actual count of the vowel, right? We just want to know whether the vowel counts are odd or even. Suppose we traverse from the start of the string, that is index 0, and we have a method which tells us whether the string we have seen so far has even or odd number of vowel count. And let's just focus on the vowel A. Now, if between indices 0 and I, we have an even number of A's, and from indices 0 to j, we also have even number of A's, then the substring between I plus 1 and j will have an even number of A's as well. For example, if substring up to I has 4 A's, here I am showing contiguous, but they don't have to be contiguous. So, if the substring up to index I has 4 A's and up to j has 6 A's, where j is more than I, that means the substring between I plus 1 and j has 2 A's, which is again even. The same reasoning applies if the substring between 0 to I and 0 to j have odd number of A's. For example, if the substring up to I has 3 A's and substring up to j has 5 A's, then the substring between I plus 1 and j will have 2 A's, which is again even. This logic holds true for other vowels as well. Essentially, we need to track whether the number of each vowel is even or odd, and when the pattern or the state repeats, we know that the substring between those indices has an even number of respective vowels. So our problem becomes simpler. We iterate from the start of the string and see whenever the pattern repeats, we know that the substring has even number of vowels. And we can then check if the substring has maximum length so far. This allows us to efficiently find the longest substring without generating all the substrings. But how do we get this flag or method that can tell us whether the vowels have odd or even count? One approach can be to use hashmap of vowel and the boolean flag. Boolean flag will be initially true, denoting the even count. And when we are iterating over the string and we see a vowel, for example A, we flip the flag, signifying that number of vowels have become now odd. And when we see the same vowel again, we flip it back to true, and so on. However, you may have guessed by now that we can actually store this information more efficiently using bit mask, since we are flipping the bits between odd and even states continuously. We will need 5 bits for each vowel to store each vowel's even and odd count state. And suppose we store the state for A at 0th bit, E at first bit, I at second bit, and so on. Each bit in the state represents the parity, even or odd, of each vowel. Initially, all the bits will be set to 0 because all the vowels have appeared 0 number of times and 0 is an even number. And suppose now we see A in the string. That means now number of A's have become odd. So how can we flip this bit? So we will just do XOR with 1. Because for XOR, when the bits are different, the output is 1. And now the bit value for A becomes 1 in the mask. And now suppose again we see A. Then how will we flip it back to 0? Because now number of A's have become even. So we will again XOR it with 1. Because now 1 XOR 1 will give us 0. So we can actually use the XOR to flip the bit. But now suppose we see E. So how can we flip E's bit? So for that, XOR at this position. And how can we get this number? We can just do 1 left shift 1, which is the position of E. So 0 XOR 1 at E's position will give us 1. And because of this, our bit mask now becomes 0, 0, 0, 1, 0. And that is a binary representation of integer 2. And suppose now we see I. Then we need this binary number. So we can again do 1 left shift 2 because that is the position of I. So if we do XOR now, 0 XOR 1 will give us 1 and so on. So basically we store this information efficiently using bit mask. And now just by looking at the value of this bit mask, we know which vowel has appeared even number of times, which vowel has appeared odd number of times. And at maximum, there will be 2 to the power of 5 such states. That is 32 because there are 5 bits and they can be either 0 or 1. So in total, we have 32 such states. For example, one state can be A occurs odd number of time, but rest of the vowels occur even number of time, and so on. But the main thing is we have this input string on which we iterate and store the state, and whenever the state repeats, we know that this is a valid string with even number of vowels. For example, A occurs odd number of times, but other vowels occur even number of times. That is one state. And if this repeats again in the string, that means the substring between it has even number of A's as well as even number of other vowels as well. And this is the idea of this problem. And we can actually use the hash map to store this state variable, and we also store corresponding initial index to mark the start of the substring. And whenever we see the repetition of the state, that means the substring between those two indices is a valid one. That is, it contains even number of vowels. And we can calculate the length of it, but we don't know if it's a maximum length or not. So for that, we will use a variable to track the maximum length. And now let's see this in action. Suppose this is our input string. I have stripped it down compared to Leetcode's example 1. Initially, our bit mask is 0 to represent the current state, where all the bits are 0, including even counts for all the vowels. Let's also initialize our state to index map containing the state and corresponding initial index when we encounter this state. Initially, it will contain the state with all even vowels, that is bit mask 0 with index value -1. So that we include the string from very beginning. We will see how the math works in a second. Initially also we will define our max length to track the length of the longest valid substring we found so far, and it will be equal to 0. We define a mapping for vowels with the bit positions. It is 0 for A, 1 for E, 2 for I, and so on. This will help us to update the bit mask. So now we start iterating on the string, and first character we see is E. This is an vowel. So that means we need to update our bit mask. So we toggle the bit at first position from left to right. And now our bit mask becomes 0, 0, 0, 1, 0. That is integer 2. And this state is not present in the state to index map. So we add it to the state map for index 0. And this one is like an invalid string because E occurs once, which is an odd number. So I have marked it with the black color. Now next character we see is L, and we can see that L is not a vowel. So we don't have to change our bit mask, and bit mask already exists in the map. That means at index 1, the state has now repeated. That means we can find a valid substring ending at index 1 but starting at index 0, which is present in the map. And this is the substring we are talking about, and the length of the substring will be 1 minus 0, that is 1. And because it is more than our previous max length of 0, now our max length becomes 1. So then next character we encounter is E, that toggles the second bit in the bit mask. So now our bit mask becomes 0 again, and we can see that 0 is already present in the state to index map. That means this is a valid string. and we calculate the length of the valid string is 2 minus 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 1, and that will give us 3. So that's how the math will work, because we are assuming even before the index start, the string is valid. And if you want to see the string, that is ELE, which is a valid substring. And now because length of current substring is more than previous max length of 1, we will update our max length to 3. Now we encounter another E. And because it's a vowel, we will again update our bit mask. And now our bit mask becomes 2 again. So we see that 2 is already present in the map and the corresponding index is 0. That means we can form a valid substring ending at this index. So our substring length will be 3 minus 0, and it is equal to 3. So it doesn't change our max length because our previous max length was also 3. And by the way, this is the substring we are talking about. Then we come to T, and because it's not a vowel, the bit mask stays the same, and the bit mask 2 is present in the map and the corresponding index is 0. So the max length now becomes 4 minus 0, that is 4, and it is more than current max length, so our max length now becomes 4. Then we come to M, that is again not a vowel, so our bit mask stays the same, and now our max length becomes 5 minus 0, that is 5. Then we encounter I, that is a vowel, so we toggle the bit at second position, and this will not be a valid string, but we have encountered a new state, that is 6. So we will add 6 to the map for index 6. And then we encounter N, and that is not a vowel. So the bit mask doesn't change, and we can see that this bit mask is present in the map. So now the length of this string will become 7 minus 6 in the map. So it will become 1, and that is not a maximum length. Then we encounter I again. So we toggle the second bit again, and now our bit mask again becomes 2. And we can see that bit mask 2 already exists in the map, and the corresponding index is 0. So now the length for the current string ending at index 8 will be 8 minus 0, that is 8. And that is more than maximum length of 5 earlier. So now our max length becomes 8. Then we come to O, and it is a vowel. So we toggle the third bit in the bit mask. So now our bit mask becomes 10. We see that this is not present in the map. So we will add it to the map for index 9. Then we encountered P, and P is not a vowel, so we don't change the bit mask, and we find the bit mask in the map. So that means we can form a valid string at this index, and the length of that string will be 10 minus 9, that is 1, which is this one, and we can see that this is not a max length. And now we have come to the end of the string, and finally we will return 8 as an answer. And in terms of time complexity, it will be O of n, where n is the length of the string, because we are just going through this string character by character and updating the max length. And in terms of space complexity, it will be O of 1, because even though we are using this extra map, we already saw that maximum number of states can be 2 to the power of 5, that is 32. So that is still a constant number. And now let's jump into the code part. So let's define our state to index map to store the first occurrence of each bit mask. And we will put state 0 map to -1, so that we handle a scenario when the entire substring is valid. Let's also define our max length to 0. That will be our answer. And our bit mask initially will be equal to 0. We can also define the character to vowels position map. This will help us to toggle the bit for a vowel in the bit mask at a specific position. For example, let's map A to 0, E to 1, I to 2, O to 3, and U to 4. And now we can start iteration on the string. We get the character at the ith position. Now, if this is a vowel, let's update the bit mask. So we will toggle the bit in the bit mask by using the XOR operation. So we will get the vowels position from the vowels map. We then left shift 1 accordingly and toggle corresponding bit in the bit mask using the XOR operation. Now if the state is not present in the map, then we will add it to the map along with the current index as we see it for the first time here. And then we will just update our max length as a maximum between whatever is the current max length and the length of the current substring ending at current position. And current string's valid length will be current index minus the first occurrence of the index when this bit mask was seen. And finally, we return the max length. Let's run this code. Okay, I think, yeah, sorry for the typo. Let's run this code again. Cool, let's submit this code. Awesome. I hope this video was useful to you. If it was, please like, share, and subscribe. The code link is in the description below. If you have any questions or suggestions, please write them in the comment box. Thank you for watching. Have a nice time.